Okay, what we had seen last time was that if A is self-adjoint, so and P is a polynomial, what we had seen was that norm of P of A is bounded by the sup norm of P over the spectrum of A. This is what we. So rather than repeating this again and again, writing the long single notation, I will use the following notation: norm P sub sigma. I'll write norm F sub x if F is a function defined on x. By norm F sub x, I would mean sup norm of F on x. Okay. So, since actually the spectral theorem is going to be valid for the normal operators, so I'd like to discuss this in slightly greater generality. So, so more generally, suppose, in fact, this will hold, this is certainly going to be less than equal to, for any sigma containing the spectrum of A, right? Because there is after all the sup over some set. If the polynomial is defined on a larger set also, then the sup on the larger set will be larger. So this is going to be true. So the fact that we actually have the spectrum of A, I want to see how that comes in a little later. For that, it helps to maybe think in slightly greater generality. So we'll assume now that sigma is some subset of the complex plane. Typically, our spectra of normal operators will be compact sets in the plane, and suppose and assume so we've got this thing when A is self-adjoint and sigma is equal to the spectrum, sigma contains the spectrum of A, and I want to say suppose norm of P of A star. So in the previous thing I was taking P to be a polynomial in one variable. Now I want to take a polynomial in Z and Z bar. That means the inner combination of Z to the J and Z bar to the K. Suppose this holds. For all polynomials of the form for all polynomials, suppose we have this relation. And for me to make sense of this rigorously, see when you write this, here Z and Z bar are commuting. What do I mean by P of A star? I will mean presumably sigma Cij A to the I, A star to the J. In general, if you take operators A and A star, they need not commute. So, whereas here this Z and Z bar are commuting variables. I want to apply it for things which might, so that I don't run into this hassle of things not commuting. I will say this only where A is normal. If A is normal, then it doesn't matter. A star, A power A star is J is well-defined object because A and A star commute. So if you take a word in A and A star, then you can always group them together so that you take bunch of A's first and then a bunch of A stars. Okay. Suppose this happens. Okay, then see, I want to appeal to the Stone-Weierstrass theorem, which tells me that functions like this, when restricted to sigma, with respect to norm sigma, are dense in all continuous functions of sigma. Right? So, what you see, if you define the mapping that sends a P to P away A star, that is clearly a linear mapping in P. And so you defined a linear mapping on a dense subspace of continuous functions on sigma, and you assume that it is a norm decreasing mapping. So it will follow that there exists a unique representation, which means star homomorphism pi from C sigma to B of H such that pi of A Z. So when I write Z, I mean the function which is the identity function on sigma. F of Z equals Z. And pi of 1 is the identity. This one is the identity operator on H, this one is the constant function 1. So this says that there exists this mapping can be extended from polynomials to all continuous functions because by Stone-Weierstrass. That mapping, I'm asking you to observe, clearly preserves products, adjoints and sums. It is a star algebra homomorphism. Right? So what we see is that under this, if you have this present situation, then you have a representation from C sigma to B of H. And conversely, if I have a representation from C sigma to B of H, and then Z is a function on sigma, and we put pi Z equals A, that A must be an operator in B of H, and if this is a star homomorphism, that means Z bar should go to A star. So I'm thinking of C sigma as a star algebra with the complex conjugation giving the adjoint. So because Z and Z bar commute, it will mean that this A must necessarily be normal if this were a homomorphism. So this happens precisely when so let me call this if not if star holds. Conversely, if that inequality, conversely, if there is a representation, there must be a normal operator A with spectrum contained in sigma. Why should the spectrum be contained in sigma? Because the star algebra homomorphism. Okay, so you think about it. with
What's the condition? A is normal. A will be normal.
no. So the statement is that there exists star homomorphism like this, satisfying this, if and only if star holds for some normal A satisfying star holds for A with such that pi of z equals A. Actually, this direction is not so important, so let's not worry about this for the moment. Okay, so my goal now is to try and understand representations of C sigma into B of H for a general sigma. Because what we've just seen is getting a representation of C sigma. See, because if you look at the function z minus lambda is going to be an invertible function for lambda not in sigma, in C sigma. Consequently, if you have a star homomorphism like that, the pi of z that A must be necessarily such that A minus lambda is invertible for all lambda not in sigma. Right? So what I am saying is that there is a one-to-one correspondence between normal operators with spectrum inside sigma and star homomorphisms of C sigma into B of H. So I repeat. So what we said is there exists one-to-one correspondence between representations pi from C sigma into B of H and normal A in B of H such that spectrum A contained in sigma and A satisfies star. In fact, you see, we proved that every self-adjoint operator satisfies star, the condition star. It is true that that condition star is satisfied by any normal operator. That we will see as we go through our Satira's book. Okay, so in a sense, in order to study normal operators, I need to study representations of such sets, such star algebras. So let us study such. So we want to. So the goal, the immediate goal, is to study representation of C sigma. Okay. In this, so the best way. So let me take the easy way out and start with an example of such a representation. By a representation of C sigma, I just mean a star algebra homomorphism into some B of H. Right? So suppose mu is a finite positive measure defined on the Borel sets of sigma. Okay, now I'm going to start using measure theory a little heavily. So, I will need you to know things about standard facts about measure theory, things like the least representation theorem and so on. I will be appealing to. Okay, suppose you have a finite measure mu on sigma, defined on the Borel sets. Then notice that in fact, so I want to define, given a function, given a good function on sigma, I want to define an operator by saying that pi f of g equal to f times g. Actually, I shouldn't say this. So pi. I want to define pi f, an operator on L2 of sigma mu. So actually, elements of L2 sigma mu are not functions. They're equivalence classes of functions. But nevertheless, if I take a representative from that class and send it to the class of f times g, then that is independent of which representative I chose. And that gives me a well-defined mapping on the set L2. And so I want to say that for good function, this is going to be a bounded operator. So for what f will there be a bounded operator? What is the norm of fg? L2. The norm squared is integral mod of g squared d mu. For it to be a bounded operator, I want it to be less than or equal to some constant times integral mod g squared d mu. Right? If I can ensure this inequality, then that f will going to induce a bounded operator. So when will this, what is an easy way to ensure this inequality? So if f is a bounded function, so if I take f in L infinity mu, okay, I'll decorate this L infinity with as much detail as I feel like at that time, sigma mu or sigma b sigma mu or just mu. So so in order for this to be a bounded operator, it must be true that norm f L infinity must be less than or equal to k. F must be essentially bounded by k. Mod f must be less than or equal to k almost everywhere. In order for this to hold for all L2 functions g. Right? So actually what one has is this pi is actually a representation of, in fact, V1 L infinity mu. On B over T. L infinity itself is a star algebra, just like C of sigma is. If you take bounded functions, that is a star algebra with a norm given by the sup norm, and you're saying that this multiplication represented by multiplication L infinity acts as operators on L2. And the multiplication representation of L infinity and hence necessarily also of C sigma, which can be thought of as sitting inside here. Does it sit inside here? What do you mean by sit inside here? Huh? What do you mean by C sigma is a subset of L infinity mu? L infinity mu consists of equivalence classes of essentially bounded functions. So every function is bounded. Right? So every function is essentially bounded, but what am I trying to say? When you say contained in, you have two abstract objects x and y, and you say x can be thought of as a subset of y. That means you must have a one-to-one function from x to y, right? So you have, what is the inclusion? Is the mapping from C0 to L infinity mu one-to-one? If sigma is 0, 1, for example, or 0, 2, and mu is Lebesgue measure on 0, 1, and 0 outside there. Then if we take a continuous function which lives outside 0, 1, L infinity mu will not see that function at all. Do you understand what the point I'm making? The point I'm trying to make is that the mapping from C sigma to L infinity mu is not in general one-to-one. Okay. But what I should nevertheless say is that independent of this statement, I can observe that there exists a representation by mu from C sigma to B of L2 such that pi mu of f is at pi f, is what I have called pi f, is multiplication by f. I am kind of being pedantic and tongue twisting, but I am saying I nevertheless have a representation of C sigma on L2 mu to any f. I associate the operator of multiplication by f.
If omega is compact, otherwise it will not be bounded.
Huh? Yeah, sigma for me, I didn't say that. Sorry, sigma is always compact. Sorry. Point well made. For me, the sigma is compact. Otherwise, the soup norm doesn't even make sense. So, if sigma was compact, and if I take a measure on sigma, then I get a representation pi mu from C sigma to bounded operator on L2, where phi mu of f is the operator of multiplication by f on L2 of mu. Right? What I said earlier was that this pi mu may not be one-to-one, but That has nothing to do with phi mu being a representation. One should nevertheless observe that the norm of pi mu f is bounded by the sup norm of f. I'm trying to say the norm of pi mu f. What is norm of pi mu f? So there is the inf of all constants for which that inequality holds. All constants k such that norm f g is bounded by k times norm g for all g. And that I at least asserted last time is the same as the L infinity mu, I want to say, the norm of the equivalence class of f and L infinity mu. Right? The norm of pi mu f is the essential supreme norm of f with respect to mu. So if it is not clear, this is an exercise. So I will make various statements like this without explicitly writing the proof. You should go and check out the proof for yourself. Okay.
So here you cannot say that norm of pi u is equals to 1.
Sorry?
Norm of the representation is equals to 1.
It is the norm of any representation is less than or equal to 1.
Here it is a pi.
And it will be equal to 1 if it is non-zero. One can prove that. If the representation is non-trivial, then you can prove that it has norm 1. So we'll see all of that when we study algebras in detail. Okay. So I've said that given any probability, given any measure mu, then I have a representation of C sigma on L2 of mu. Now, conversely, I want to ask, what is special about these representations? If you look at the representation pi mu, so I ask you to note that pi mu is, the crucial fact is that pi mu is a cyclic representation. What that means is, i.e., pi mu has a cyclic vector in fact, the vector x the constant function 1. What I mean by cyclic vector is, if you have a representation pi mu of A, of an algebra A, then that means that, okay, let's write some notation. If A is an algebra, if X is a subset of Hilbert space, then I'll write square box S equal to the closed subspace generated by S. You take the linear span of S and take the closure of that subspace. It is not clear, is it? So what this statement means is that i.e. So we'll say that psi is a cyclic vector for representation pi if, so here pi is some representation of some algebra into B of H. And there is some algebra. If I take pi away times xi, that means if I take the set of all pi away acting on xi, k in A. Equal to H. That means if I move that vector around by the algebra, then I get a space, I get all of H. The closed subspace generated by that vector is this H. So see, you must look, all the terminology is from finite dimensions. See, if you take finite dimensions, for example, if you take this operator, if I take this operator A, and if I take the algebra generated by A, what is the algebra generated by A? It is just polynomials in the day. Okay. So this thing, if you cube it, you will get 0. So there is just all those things in the form from A0, A1, A2. Then the polynomial is summation aj t to the j. If I apply that polynomial to this operator, you will get exactly this thing. I don't know, there are too many years. I will call this C0. This is not to be confused with this operator. Okay, anyway, the polynomials in this. And so, see, the point is that I am saying that the first basis vector is cyclic for this algebra. If you take this operator and act on it by all things like this is from the 0. We act on all such matrices on this thing, then I'll get all of C3. Right? So this one is a cyclic vector. What it means is that if you take xi, a squared xi, and so on, those things will span the entire vector space. In finite dimensions, this is what it means. In infinite dimensions, what you want to mean is that if we take the powers of A acting on xi, they must span out the entire Hilbert space. Okay, so why am I doing this? Since I'm talking about star algebra, a normal thing, that may be a little more fussy. So I want to say conversely. So that what I did earlier was an example. I said if you take a representation mu, if you take a measure mu on sigma, then pi mu gives an example of a representation of C sigma, which has a cyclic vector. Because the constant function 1 is cyclic for that thing, because C sigma is dense in L2 sigma. Okay? Okay, there is a statement of density. So conversely, I want to say every cyclic representation of C sigma arises and is a pi mu. That is, there exists some measure mu, so that it can be recognized, identified as pi mu. Now, why is this true? Because if proof, if pi is a cyclic representation, with cyclic vector psi. So what does that mean? That means that pi of C sigma, in fact pi of okay. So this is what we are saying. Okay. What does it mean to say that every cyclic representation is a pi mu? Here we are given an abstract Hilbert space on which the pi represents. Now I am saying that H, I cannot say that H is actually equal to an L2 mu. I can only say there is a unitary operator which by H can be unitarily identified with an L2 mu in such a way that this representation is identified with pi mu. Right? So I need to get a unitary operator between this H and L2 mu for some mu. So for that there is a little lemma. Which has always been emphasized by K. Do all of you know who KRP is? You know the name KRP? KR Parthasarathi. So anyway, he is a So he is a man from whom I've learned a lot of mathematics, and so he would always emphasize the importance of this lemma. So I think of this as the KRP lemma. Okay. So not that he proved it, but he always says, this is at the essence of so many different things. Okay, so what does it say? So suppose I have two sets. Suppose I have two Hilbert spaces HI, and I have two sets SI. Okay, okay, incidentally, one says that a set with the property that box S is H, one usually calls the total set in H. One expresses this by saying Si is total in H. This phrase means that as a closed subspace it spans all of H. For example, Si could be an orthonormal basis, or it need not even be an orthonormal basis. It can only be some linearly independent set to which, if you apply Gram-Schmidt, you will get an orthonormal basis for the entire Hilbert space. So it can be okay. So suppose you have two total sets in the Hilbert space, and suppose both the sets can be indexed by the same family. That is, suppose I have both sets have the same cardinality. They have the cardinality of this lambda, and I can index the sets Si by lambda. That's what this says. Okay. Suppose you have two sets like this, and suppose more. Suppose these total sets have the property that if x1j, x1k equal to x2j, x2k. Or in other words, what I am saying is, suppose I have a mapping. See, if you look at the mapping that sends x1j to x2j, so you have an association from one total set to another total set, which is inner product preserving. So if you have an inner product preserving identification of a total set here and a total set there, then such an identification will extend to a unitary operator between the Hilbert spaces. There exists a unitary U from H1 to H2 such that Ux1j is equal to x2j. And inner product preserving bijection between total sets will extend to a unitary operator between them. The proof is more or less obvious, right? what should you do to prove this thing? By definition, you want to define U on all of H1. What do I know about H1? I know that it is the closed span of S1. So if I take linear combination of S1, that is dense in H1. So take linear combination in H1, and I just send the map. This U must send that map, that linear combination, to the same linear combination in S2. And it is a trivial exercise to verify that this thing, because the inner product is linear, it will extend to this, the map that you defined on the span of S1 to span of S2 is inner product preserving from one dense set onto a dense set, and hence it will extend uniquely to a unitary operator from H1 to H2. Right? So there is really nothing much to this theorem, but it is a very useful theorem. Okay, so let's see how we are going to use this theorem. So, see what we know. Some number is in trouble with this. Okay, now we are now coming back to the theorem that I want to prove. So we are given a cyclic representation. So proof of the proposition. So we are told that pi from C sigma to B of H is a cyclic representation. What does that mean? That means that, therefore, if I look at all things of the form pi z to the I, pi z bar to the, maybe it will be better if I write this way, z bar to the j, z to the I. Psi is total in H. Right? Because monomials like z to the I, z bar to the j are dense in C sigma. And hence, if you are told that, see, by representation you mean something which is okay, yeah. So representation means a continuous star homomorphism. Actually, continuity will come for free, as we'll see. So if a sequence of polynomials converge uniformly to continuous function f, then pi pn must converge to pi f in norm. And because polynomials are dense in C sigma, it will mean that pi of such monomials will be dense in the image of pi C sigma. So the assumption of cyclicity of the representation is exactly the statement that these things are total in H. Okay. No, they're not body. So we'll come back to this. We'll come back to this later. So I want to say consider the mapping. Phi mapping C sigma to C defined by phi of f equal to pi f psi psi. Everything is defined, right? Pi f is an operator on H. And I just evaluate this inner product on that. So what I observe is that phi is continuous, it is linear, it is a linear function on C sigma, and it is positive. What does that mean? That means that phi of mod f square is non-negative, which is phi of f bar f. Right, which you can write as pi of f bar f psi psi, and pi is a homomorphism, the star homomorphism. So you can write this as pi f star pi f psi psi, and you can write this as pi f psi pi f psi. So it is non-negative. So you have a positive linear functional on C sigma. And this is what Rees has something to say about. That every positive linear function on C of sigma, where sigma is compact, arises by integrating against a finite positive measure. So the conclusion is so the conclusion is, therefore, there exists a positive measure mu defined on the Borel sets of sigma such that pi f phi f is integral f d mu. See what this says about phi of G bar f. So see, on the one hand, this is equal to pi of G bar f psi psi. So this says that pi of psi pi g psi equals integral of fg bar dv. So we are in exactly the situation that the KRP lemma is wanted. See, here the F's range over the continuous function of sigma, which is a dense subspace of L2. Here the pi of sigma size range over a dense subspace by hypothesis of cyclicity. So the conclusion is, so the KRP lemma implies that there exists unique unitary from H to L2 mu such that U of pi of z equal to F. Here I'm being sloppy. On this side F is actually a continuous function. On this side actually F is an element of L2 mu. So I should probably write this. And now, so a little exercise. So if you so I want to say that in fact exercise. I want to say that the pi is a representation here. So U pi f U star. So pi f are operators on H. By conjugating by U, I'll go over to operators on L2 mu. So I'm saying that this is exactly what we call pi mu of X. This verification you will be able to, and everything is there in front of you, so you just have to dot the i's and cross the t's. So we've shown that in fact if pi is a cyclic representation, then it comes from a measure mu in this fashion. Okay. So let me stay at the cyclic case for just 2 minutes more. In the I want to see when pi mu f for any continuous function, I want to see what is the spectrum of pi mu f. That is for what lambda is. See, I want to say lambda belongs to sigma pi mu f. So when does this happen? See, we know that all for here f is a continuous function of sigma, right? We know that pi mu f is actually normal, right? Because this pi mu is a star representation, so the adjoint of pi mu f is pi mu of f bar, and f bar commute, so pi mu f and pi mu f bar commute. So this is a novel operator. Now we've seen that something is points in the spectrum of a normal operator are approximate eigenvalues. So it is, let me put it, it is not in the spectrum if and only if pi mu f minus lambda is not bounded below. Then think of what it says to say lambda is not an approximate eigenvector. Huh? Is not in, sorry, so not in means is bounded below. Because if it is not bounded below, then for every n there will be psi n because the norm is less than 1 by n and so on. So this means they are bounded below. So what does that mean? This means that there exists a positive epsilon such that if I take the measure of result of all z such that altitude of z minus lambda is less than epsilon equals 0. Go to the next case. To say it is bounded below means exactly that epsilon ball about lambda must have 0 measure. That means that this really amounts to saying that 1 over f minus lambda is greater than or equal to epsilon almost everywhere. The measure where mod f minus lambda is less than epsilon is 0. That means where 1 over mod f minus lambda is greater than or equal to epsilon must be everything. That means f minus lambda is invertible in L infinity. Right? If and only if f minus lambda is invertible in L infinity. See, you must be careful that I haven't had a chance to make a noise about this. See, when we talk about spectrum, that is, one has to be careful. Namely, okay, so let me diagram. This is an important point. I think one should let me digress for a minute. See, suppose A is a Banach algebra. With a unit. Then it makes sense to talk about the spectrum of something here. And what do we mean by the spectrum of, and suppose I take an x in A, then I've been happily saying spectrum of x is all those lambda in mu in C such that x minus lambda is not invertible, is not invertible. What do I mean by not invertible? That means not invertible in this algebra A. So let me play devil's advocate for a moment and say that I should actually call this sigma A of x, because it is something which depends on A because it is conceivable that in fact 1 and x belong to some B which is, you may have a Banach subalgebra of A. Now it is conceivable that sigma B of x, now why should this be equal to sigma A of x? If this x was invertible in B, then of course it will be invertible in A. But if it is invertible in A, why should it be invertible in B? It is conceivable that you might have such a situation where you have an invertible element of the big algebra, but whose inverse is not in the small algebra, which means that 0 will be in the spectrum of one, but it will not be in the spectrum of the other. Right? And the classic example of this is the following thing. So you look at who is there who? And they so for A, I take the continuous function on the unit circle. There is a complex unit complex numbers. Set of z with mod z equals 1. Okay. Now for B, I want to take the so-called disk algebra. What is this? This is equal to all those functions which are continuous in the closed unit disk and which are holomorphic in the interior or analytic, whatever you know. I want functions which are analytic in the interior and which extend to continuous functions on the whole thing. Now, see, by the maximum modulus, see there is a natural mapping from B to A. You take such a function, you restrict it to its boundary values. Then you get a mapping from B into A. Now the crucial thing is that this is an isometry. That is, both B and A have the soup now. Why is it an isometry? Which theorem tells you that this is an isometry? Maximum modulus principle for holomorphic functions. If I have a holomorphic function in this, it will attain its maximum modulus on the boundary. Okay, so the maximum modulus principle will tell you that this mapping is an isometry. So I can think of B as a subset of A. Now I can look at the function f of z equals equals z. It is invertible in A, because in A the invertible functions are the functions which are not zero anywhere on the surface. But it is not invertible in B. So I am saying 0 is in sigma B of f and not in sigma A of f. So in general, when you talk about glibly about spectra, they do depend on which algebra you are talking about. But it is a fact that in the category of C star algebra, see, the problem here is analyticity, because the complex conjugate is not an analytic map. To get all continuous functions, you need to use polynomials in Z and Z bar. But the Z bar is not a holomorphic function. And the moment you throw in, you are allowed to throw in that bar, the moment you get into the C star context. So I am saying there is a theorem that says that in this, if I replace Banach by C star, then the two are the same always. So what I am saying, coming back to our theorem here, was that if you take an f in C sigma, and if you apply pi mu f, each spectrum as an operator, now you can think of pi mu f as an element of L infinity, or as an operator on L2. Do you understand what I am saying? If you look at L infinity mu as bounded operators on L2 by multiplication. So L infinity, so I am saying, see, L infinity mu can be thought of as sitting in ZB over L2 mu. Now what I said showed in the previous slide is exactly that if I take something in, actually this doesn't even have to be in C of sigma. Okay, so let me not take L infinity mu, but let me look at pi mu of C sigma. I can look at the spectrum of pi mu f, or I can, in fact, Again, the various things happening here. Actually, pi mu of C sigma can be thought of. So by the same token, I have a representation of, I call it pi mu tilde of L infinity. L infinity can also be thought of as multiplication operator. But think of that representation of L infinity as pi mu tilde. So see, so this is certainly contained in this image, and this is contained in B of L2Z, L2 sigma. Now what I have said over here is that if I take an element here and if I compute the spectrum here, that is the same as the spectrum in L infinity. And in fact, we'll see that to make this thing complete, let me say, observe the following thing now. I want to say that in fact, I'm going to say something that I cautioned you against saying. So, for a moment, let me pretend that C sigma is sitting inside L infinity mu. It is not sitting inside injectively, but you know what I mean. So what I want to say is that, see, I have a representation pi mu is a representation of C sigma and B of L2 mu. Okay? Now this has the following property. Pi mu extends to the representation pi mu tilde there I put a tilde somewhere has been of L infinity in such a way that whenever Fn converges to F as in dominated convergence theorem. So what I mean is, i.e., suppose I have a continuous function Fn and suppose mod Fn, and let's say as in bounded convergence, Fn equal to k for all n. You have a sequence of uniformly bounded continuous functions and which converge pointwise. See, initially when I said representation, that just it carried norm convergent sequences of functions to norm convergent sequences of operators. But now I want to say that whenever this happens, pi mu tilde of Fn converges to pi mu tilde of F and this strong operator topology. This is just the dominated bounded convergence theorem in disguise. I'm just saying it in fancy language. What am I saying? We take any G in L2. I want to say that Fng converges to Fg in L2. And that is what the bounded convergence theorem tells you. So this cyclic representation pi mu. So I want to go back and see the following. So I have noticed that if I have any cyclic representation of C sigma, then it corresponds to some pi mu in fact. In fact, what this says is that such a cyclic representation extends uniquely to an appropriately continuous representation of L infinity mu for some mu. So I snatched the mu out of the hat from the representation. From the cyclic representation, I have in fact a representation of a larger algebra which respects this kind of convergence. It translates bounded convergence to strong operator topology convergence. And we are very close to stating the
This means pi mu is continuous in the if you do the topology of this convergence.
pi mu is continuous with what?
Means if you give convergence as this one on both sides, the strong operator version, the codomain and the convergence like this on the domain.
Except this is not quite a topology. Right? So one must check this thing carefully. Actually, the correct way of saying this is that that requires the language of one-number algebra. The correct way of saying this is there is a topology on L infinity mu, namely the B star topology coming from L1, which you get. And so in terms of that, you can make a topological statement of the convergence. We will come to that when we get to one-arm algebra. Okay, so
This is a statement.
huh?
You are defining pi mu intelligence. You are
Yes, so I'm saying that, okay. So one saying, in fact, pi mu extends to a representation of an L infinity mu.
how pi mu tilde is defined? We have pi mu. How?
So I'm saying pi mu tilde on L infinity given by multiplication representation. But I'm saying if I see, in fact, I can use this to define it in view of Lusin's theorem, which tells you that you give me any bounded function, bounded measurable function, then I can find that at the point-wise limit of continuous functions almost everywhere. And I can choose those fn's continuous to also have sup norm less than or equal to this. I can find them uniformly bounded. So given anything in infinity, I can find a sequence of continuous functions which approximate that point-wise in the sense of bounded convergence. And then I'm saying that in what I'm saying is that in such a case, automatically it will follow that pi mu fn's will converge in the strong operator topology. And that strong operator limit will be unique. And I can define that as the image of this function f. So, but everything, is transparent when you have the mu in front. It is the representation of L infinity mu given by multiplication. That is what we are talking about. Okay, so okay, let me go over a little because next time I want to start with Satyajit properly. So the point that one wants to make is the following. See, if you have, suppose now that pi is any representation of C sigma. Okay. Then I can represent see you can do the following thing. You use Zonstrom or whatever. We'll assume that representation on separable Hilbert space. Okay. Okay. Then I want to say you can do the following thing. Take any vector in each and look at the cyclic subspace that generates for this representation. Now there will be some subspace H naught of H. If H naught is H, I'm happy, I go home. I've got measure mu. Otherwise, see, H naught will be an invariant subspace for this representation, for this algebra. So all the C sigmas act as normal operators. So there is a pi of C sigma will be a star algebra of operators, and if they leave some subspace invariant, they will leave the orthogonal complement also invariant. So first I look at some psi 1 and look at the cyclic subspace generated by psi 1. And then I go to the orthogonal complement of that subspace. I take some psi 2 there and sweep out its cyclic subspace. What I get will be something orthogonal to the initial subspace. I have two cyclic subspaces which are orthogonal to one another. If they don't exhaust everything, then I take one more. And then and keep on doing this means you apply Zon. With Zon's lemma, I can get a maximum collection of pairwise orthogonal cyclic subspaces inside this Hilbert space for this representation. Because this Hilbert space is separable, such a collection must be countable. So what we find is that H can be written as direct from N. I'll make this kind of fast, all they will make precise later. L2 sigma mu n. I can exhaust H by, I can write H as the direct sum of cyclic subspaces. Each of those subspaces, if I restrict my representation, what I have will look like this.
Unitary U.
Yeah, so what I'm saying is there is a unitary U, there exists unitary U from H to this Hilbert space direction such that U pi U star will be direct sum over n pi mu n. Okay, maybe I'll. Okay, this two. I shouldn't kind of push this under the. But on the other hand, I don't want to waste time next time. Okay, so this means that pi. If I look at pi away is going to be unitarily equivalent to direct sum n pi mu n of. So in this I have assumed that this. So A was my normal operator with spectrum sitting inside the sigma. So I'm looking at that thing. So that looks like pi mu n of z. Right? I look at the normal operator which corresponds to that z. So I look at the generator of the C sigma, see where it goes under this representation. And so what I find from what I've seen before is that the spectrum or the norm of pi A is going to be, if you take a direct sum of operators, what is the norm of that? Huh?
Square of something, square of half.
If you take a diagonal matrix, what is its norm?
Maximum.
So we take a direct sum of operators, we take direct sum an. It will be the soup of the norms. The operator norm, no? If you have a direct sum of operators on Hilbert space, uniformly bounded, then the operator, the norm of the direct sum operator will be the soup of their operator norms. Okay, I guess I have to give in. Okay, some other time I will complete the story. So see the point one, so I'll just write two lines, I'm too close. You have a sequence of probability measures. Now I can define a new probability measure, summation 2 to the minus n mu n. So then, see this, what we saw was that this is the soup of norm of z in L infinity mu n. Okay. But so there is another little exercise that this is the same as norm of z L infinity mu. So finally, see what one gets out of this whole thing is that if you take any representation of this C sigma, you magically you get one measure mu, such that in fact okay, when we do one hour algebra, I'll get to. In fact, what I said before says a lot more. It says that the one-Neumann algebra generated by pi mu of C sigma is L infinity of mu. Because you're saying you can approximate those by things from. Okay, I'm trying to say too much here. Let me just stop here. The point one wanted to make was that the one-Neumann algebra generated by the normal operator A can be identified with L infinity mu for some measure mu, and then there is part of the data. To complete the spectral theorem, I should tell you the spectral multiplicity. There's another whole story, so I won't even start on that. Okay.